Okay, so in this problem we have a differential equation, and the question is to find two linearly independent power series solutions to this differential equation. Let's go through it very, very carefully. So I'm going to go ahead and put a little box up here to indicate that this is the question, and everything else that will follow is the solution. This is a really long problem. So the first step always in these problems is to start by letting y be equal to an infinite sum. So y will be the sum as n runs from 0 to infinity of c sub n x to the n. The next step is to take the derivative of y as many times as necessary. So in this case, we have a second derivative, so we need to take the derivative twice. So y prime is equal to the infinite sum as n runs from 1 to infinity, and I'll come back and explain that in a minute. The c sub n is a constant, so it hangs out. So you bring the n down, so you get n c sub n, and then you subtract 1 from the exponent, x to the n minus 1. So the reason we start at 1 is because when we differentiate, the 0th term goes away. If I were to plug in 0 into this formula for y, I would get c sub 0, x to the 0. Then if I plug in 1, I get c sub 1, x to the 1. X to the 0 is 1, so when you differentiate this first piece, it goes away. It's a constant because c sub 0 is a constant. So the 0th term vanishes, so you start at 1. Then we take the derivative again. So y double prime is equal to infinite sum, and this is going to be 2. For the same reason, you can check. If you plug in 1 here, you'll get 1 minus 1, so you get x to the 0. So your first term again is a constant. It vanishes when you take the derivative, so you shift up. In general, in these problems, you always just shift up every time you differentiate. This time we bring down the n minus 1, so we get n minus 1, c sub n, x to the n minus 2. Okay, good stuff. So that's the first step, always in these problems. The next step is to plug all of this into the differential equation and simplify. So let's do that. So we have x minus 1, so x minus 1. Then we have the second derivative, so I'll write that down, infinite sum, n equals 2 to infinity. Then we have n minus 1, c sub n, x to the n minus 2. That's the second derivative, plus y prime, which is infinite sum. I'm writing kind of small, apologies. I'm trying to make this all fit. That's a challenge. N, c sub n, x to the n minus 1. And this is equal to 0. Let me just pause here for a moment and double check that I did everything correctly. It looks okay. I plugged in the second derivative for this piece here, y double prime, and then plugged in the first derivative. Everything looks okay. This pesky x minus 1 means we do have to break this up. So we're basically going to distribute. So we get to write this as x, infinite sum, lots of writing, n equals 2 to infinity, n minus 1, c sub n, x to the n minus 2, then minus, and then the same thing, n equals 2 to infinity, and n minus 1, c sub n, x to the n minus 2. And then we have the last piece there, plus infinite sum, n equals 1 to infinity, and c sub n, x to the n minus 1, and that's equal to 0. You know, when you're doing these problems, if you're feeling discouraged because of how long it takes you, just know that you're not alone, right? These problems take an incredible amount of time. It's not unreasonable for one of these problems to take you over an hour the first time you're doing it on your own. It's okay if it takes you a long time. It's normal. Now we're not quite to the next step yet. We still have to simplify. So this x to the 1 here, we're going to distribute this here. And so what's going to happen is you'll get x to the 1 times x to the n minus 2. So we're going to add the exponents. That's going to give us x to the n minus 1, because 1 plus minus 2 is minus 1. So this is infinite sum, n equals 2 to infinity, and n minus 1, c sub n, x to the n minus 1. Again, we're adding the exponents. X to the 1 times x to the n minus 2 is x to the n minus 1 minus infinite sum as n runs from 2 to infinity, n minus 1, c sub n, x to the n minus 2. Then we have this last piece here, plus n equals 1 to infinity, trying to go faster, and c sub n, which I don't know if it's a good idea for me to go faster. Whenever I try to speed up these problems, because these videos are so long, I always mess up. So let me just pause here for a moment. Everything looks okay. Okay, the next step is always the same. And I say that because we're going to reach a point where there's two possible approaches to do the problem. But so far, all the steps are the same. You always do these steps when you're using series to solve D's. Everything is the same for all the problems. The next step, which is always the same for all the problems, at least the way I do it, is I call this piece here K, I call this piece here K, and I call this piece here K. You might say, well, how can you call them all K if they're all different? It's just a dummy variable. K only has meaning within this sum, within each individual sum. So K equals n minus 1. And then you solve for n, so you add 1 to both sides, so n is k plus 1. You do it again over here. K is n minus 2. We're basically shifting the index. We want to make all of these k's. And then n is equal to k plus 2. And then here k is n minus 1. And so n equals k plus 1. Good stuff. All right. Some people do the shifting in their head. I don't like to go there. All right. So we have infinite sum. So let's see. When n is 2, so you take the 2 and you plug it in here to get your k, okay? So it's 2 minus 1, so k is 1. Okay? And then here we go to infinity. And then n is k plus 1, so this will be k plus 1. And then k plus 1 minus 1 is just k. And then we have c sub n is k plus 1. Then we have x to the k. All right, so just we carefully replaced all of the n's with k plus 1s. Looks okay. Minus infinite sum. When n is 2, you plug it in here, you get k equals 0. Beautiful stuff. To infinity, n is k plus 2, so we have k plus 2. K plus 2 minus 1 is k plus 1. C sub k plus 2. And then x to the k, which was the whole point. Plus infinite sum. When n is 1, you plug it in here, you get 1 minus 1, so you get k equals 0 to infinity. N is k plus 1, so you have k plus 1. C sub k plus 1. And then x to the k. And all of this is equal to 0. Good stuff. So far, so good. Let me just look it over and make sure everything's correct. N is k plus 1, k. Everything looks pretty good. At this point, the next step, always, is to make them all start at the same number. So this one starts at 1, this one starts at 0, and this one starts at 0. You want to make them start at the highest numbers. You want them all to start at 1. So what you do is you plug stuff into the other ones to make them start at 1. So like this starts at 1, this starts at 0. So what we'll do is we'll take the 0, we'll plug it in here for all the k's. And then we'll start the sum at 1. Because that's the same thing, right? This sum is the sum of all of these terms from 0 to infinity. So we'll plug in the 0th term, and then we'll write the sum from 1 to infinity. Likewise here, we'll plug in the 0 and write the 0th term, and then write the sum from 1 to infinity. So let's go ahead and write the sums from 1 to infinity, and then plug in the 0th terms at the end. So check this out. So k equals 1. You'll see what I mean once I do it. So this one stays the same. So k plus 1, k, ck plus 1, x to the k, minus, and then this one will be k equals 1 to infinity, because we're starting it at 1, k plus 2, k plus 1, c sub k plus 2, x to the k. And this one here, same thing, we'll start at 1, so plus infinite sum, handwriting's deteriorating, k equals 1 to infinity, k plus 1, c sub k plus 1, x to the k. So these obviously are not equal. So now we're going to plug in 0 to this one here. So it'll be 0 plus 2, 0 plus 1. So it'll be 2c2, right? Because it's 0 plus 2 here, 0 plus 2, so c2, x to the 0, which is 1. So this will give us 2c2 when we plug in 0 for the k's. This other one will give us c1, right? c1, because it'll be 0 plus 1, and then c sub 0 plus 1, so c1, and that's equal to 0. Now we can finally combine all of these sums because they all have x to the k's. You see x to the k, x to the k, x to the k, and they all start at the same number. So we have the infinite sum as k runs from 1 to infinity. I'm going to put a bracket here, and I'm going to factor out everything. So we have this piece here. So k plus 1, k, c sub k plus 1, minus, this is fun, you know, I have not done this problem before making this video, so this is really interesting. So k plus 1, so I'm trying to be really careful. It's already been 11 minutes in, plus k plus 1, and then ck plus 1. And then this is x to the k, and this is plus 2c2 plus c1, and this is equal to 0. All right, now what you do is you realize that this is equal to 0, so that means that this coefficient must be 0, and this must be 0. This is the constant term, right? This is really 0, 0 plus 0x plus 0x squared plus ... So if you equate coefficients, if you use matching, all of the coefficients are 0. So k plus 1, k, c sub k plus 1, minus k plus 2, k plus 1, c sub k plus 2, plus k plus 1, c sub k plus 1. Let me just make sure I wrote all that down correctly. Yep, and that's equal to 0. And this is for k equals 1, etc. This is really important. This tells you where to start. And then we also have this piece here equal to 0. So we have 2c2 plus c1 equal to 0. It's important to set the whole thing equal to 0. All right. So now what we do is we always solve for the one with the highest subscript. So in this case, that would be c sub k plus 2. I'm going to switch colors here. I'm going to go back to green. So we're solving for this one, okay? So I'm going to, I guess I'm going to subtract away these. Okay, I'm going to subtract these away. So we have negative k plus 2, okay, k plus 1, c sub k plus 2 equals the negative k plus 1, k. Oh, look at that. Oh, that's, I just realized something. Oh, never mind. I thought these were the same. They're different. Minus, they're close. K plus 1, c sub k plus 1. I didn't realize one of them has a k and one of them doesn't. Let's go ahead and divide by this. So we have c sub k plus 2 equals. So dividing by this whole piece here, that's going to give us k over k plus 2, c sub k plus 1, right? Because we're going to lose the k plus 1 there, and then plus, looks like we're going to have 1 over k plus 2, c sub k plus 1. So we can rewrite this in a better way. So c sub k plus 2 is equal to k plus 1 over k plus 2. That feels much better. C sub k plus 1. So that's called the recurrence relation. That's what we wanted. And notice that you just always solve for the one with the highest subscript. And this is valid for k equals 1, 2, etc. So this is important. Here, same thing, you solve for the one with the biggest subscript. So subtract C1, divide by 2. So C2 is negative 1/2 C1. I'm going to put this in a box as well. Okay, let's pause here for a moment. So now the strategy can go two ways. You can take the direct approach, which basically means you just plug in numbers starting with 1, because this is a 1, and you just try to find two patterns at the same time, and you hope it works. And there's the indirect approach, where we use this fact here. I'm going to write this on the top right of the screen so you see it. The final answer to this problem is going to be c sub 0 y1 plus c sub 1 y2, where these guys, these little c's, are from the power series. Okay, this is super important. So you can manipulate these temporarily. For example, if I were to set c sub 0 equal to 1 and c sub 1 equal to 0, and say, why am I doing that? You'll see. If I do that, if I say, hey, you know what, I want to do that, I get y equals y1. So if I do that, I get y equals y1. If conversely I set c0 equal to 0 and c1 equal to 1, what happens? The c0 goes away and I get y equals y2. So if we do these things, we will get these results. And that's what the question wants, right? The question wants the independent solutions. It wants y1 and y2. So we'll take this, which I like to call the indirect approach. I've made up this name. It's totally made up. I call this the indirect approach to solving power series. So if you manipulate your c's in this fashion, you will get two linearly independent solutions, and that's what we want in this problem. So whenever you're asked for linearly independent solutions, in my view, this is the best way to do it. So let's do that. So first, let's take this case here. Okay, so we're going to take this case here, and we'll try to, that will give us y1. So I'm going to stick to red. I'm going to look a little barrier here because I'm worried about running out of room. And let's go with that one. So C0 equals 1. C1 equals 0. We're taking this one, and this is going to give us y1. Well, notice that we have this relationship here. So that means that C2 is going to be negative 1/2 C1. Oh, but C1 is 0. That's kind of nice. So that's 0. So C2 is 0. What about C3? Well, let's see. Now we use k equals 1. So when k equals 1, we get to use our formula, which is over here. That will give us C3, because 1 plus 2 is 3. So C3 is equal to, well, we plug in 1 for k. Notice I wrote k equals 1 on the screen, because if I don't write it, I'll mess up. So 1 plus 1 is 2. 1 plus 2 is 3. And then we have 1 plus 1, which is 2, so C2. Oh, but look, C2 is 0, so this is 0. So C3 is 0. If you plug in k equals 2, you'll get 2 plus 1 here, so you'll get C3. But C3 is 0. In fact, they're all going to be 0. So C4 equals C5 equals ... They're all equal to 0 from this point on. So we're pretty much done with this case. The only one that's not 0 is C1. So now we're going to get y1. So if you go back to the very beginning of the problem, you go way back up here. Wow, that was a long time ago. 18 minutes ago, right here. This one right here, this red one. That's what we started with. So if you write that down like the long way, like if you just write it out like this, I'll do it here. Y equals C0 plus C1x plus C2x squared. That's what it looks like when you write it out the long way, right? Like not the summation notation, the long way. Now you plug in your c's. By the way, this is y1. So then y1 is equal to, well, C0 is 1, and the rest of them are 0. So y1 is equal to 1. That is our first answer, right? That is our first answer. It only took 19 minutes and 19 seconds. That is our first answer. And again, the secret to this method is knowing what's up here that I've written in the top right. This is the most important thing that you should learn from this video, is that if you do this, this will give you the linearly independent solutions, right? It's beautiful. It's absolutely awesome. Okay, so now we are going to attempt to find y2. So to find y2, I'm going to go to a different color. Let me see if this one's okay. Yeah, it's pretty good. Let's go with blue. we're going to use the other condition, this one here, which I've circled in blue in the top right of the screen. So C0 equals 0, C1 equals 1. Okay, so now we're going to find C2. So C2 is negative 1/2 C1. Okay, C2 is going to be negative 1/2 C1. Oh, you know what? I feel like there's a slight mistake here. Yeah, there is. There is a slight mistake here. This should be negative. This is a negative. So this is negative. So this is positive. Okay, so this is a positive. So little mistake there. Yeah, so if you were watching this video and you saw the mistake, yeah, okay, it's been corrected though. So this will be a 1/2 times 1. So it's 1/2. So C2 is 1/2. Okay. So it's because of this negative here, right here, that that became negative. Notice how it didn't affect our first answer, though. The first answer is actually still correct. Okay, to find C3, we plug in k equals 1, and so we get C3 equals, so it'll be 1 plus 1, which is 2, over 3, and then we have C2. So that's 2/3 times 1/2. So that's going to be 1/3. So C3 is 1/3. So how do we know when to stop? Well, we don't. We just do a couple more and, when we call it good. In this problem, we're not looking for a pattern. We just want the solutions. We're not, it doesn't say, write in terms of familiar functions. It just wants the first few terms. So let's do one more. When k equals 2, it gives you C4. So you get 2 plus 1, which is 3, 2 plus 2, which is 4, and then you get C3. And C3 is 1/3. So this is 3/4 times 1/3. So you get 1/4. So that's C4 is 1/4. That should be good. Let's go ahead and write down y2. So y2 is C0 plus C1x plus C2x squared plus C3x cubed plus C4x to the 4th plus dot dot dot. Okay, so this is y2 is equal to, well, C sub 0 is 0. C1 is 1, so we just get x. C2 is 1/2, so we get x squared over 2. C3 is 1/3, so we get x cubed over 3. C4 is 1/4, so we get x to the 4 over 4 plus dot dot dot. And that should be the final answer. So that's y2. And then here is y1. So that's it. Those are the correct answers. I actually have the answers here. I just don't have the solution. That's how I was able to find my mistake. 23 minutes. So hopefully, yeah, hopefully this video has been helpful in some way. If you're learning differential equations, I hope this has helped you. So yeah, it takes time and it takes practice to get good at this. So don't give up. These problems are long, and yeah, that's it. Take care.